This question is addressing overtones on a flute. To solve this problem, first we have to understand that audible range is from 20 Hz to about 20,000 Hz. From here, we're going to determine the number of overtones based on the fundamental frequency. We're going to solve for the fundamental frequency, and eventually we're going to divide the top audible range, 20,000 Hz, by the frequency that we get. To find fundamental frequency, we use the equation V equals 331.5 plus 0.6 times temperature. We already were given the temperature in the problem as 25 degrees Celsius. So what we're going to do is simply put the temperature into the equation and solve it. This will give us a total of 346.5 meters per second as our speed. Our next step in this problem is going to be finding the frequency, and we're going to use the equation that goes with wind instruments. This would be the frequency equals n, which is the number of the harmonic times velocity, which we just solved for, divided by 2 times the length of the instrument. We're going to use 1 for the value of n because it's the first harmonic. So we have F equals 1 times 346.5 divided by 2 times the length that was given in the problem of 0.66 meters. We're going to solve this to get a frequency of 262.5 Hz. Our last step in this problem is going to be finding the number of overtones. So we're just going to take 20,000 Hz, which is the highest audible frequency, and divide that by the frequency that we solved for originally. This will give us a total of 76. But since the first harmonic is not an overtone, we cannot include that, so we just have to subtract 1. So 76 minus 1 is going to give us 75 overtones. In this problem, we're looking for the length of the string and the wavelength on this string. To find the length, we're going to use the equation frequency equals n, number of harmonic, times velocity, divided by 2 times the length of the string. But since we're missing 2 variables in this problem, we have the frequency and the harmonic, but don't have length and speed. We can use the frequency of the original note at 330 Hz to solve for the speed on the string. This speed will not change when you change the length of the string, because the speed on a string depends on tension. Changing the length of the string doesn't change the tension, so the velocity will stay constant. We can use the frequency equation to solve for the speed. Frequency is given 330 Hz equals 1 times V over 2 times 0.68 meters. This will give us a speed of 448.8 meters per second. Next, we just plug that into the same equation, but with the frequency of the new note at 440 Hz to find the length of the string at this note. So here we'll have frequency equals n times V over 2L again. Frequency is 440 equals 1 times 448.8 over 2 times L, which is what we're solving for. This will give us a length of 0.51 meters. Next, finding the wavelength is simple. We're going to use velocity equals frequency times wavelength. The velocity is what we solved for first, which is 448.8 meters per second, and the frequency is at the new note, 440 Hz. Using simple math, we find wavelength is 1.02 meters.